Hello, welcome to this webinar on storage with Kubernetes on AWS, presented by CoreOS. My name is Luis Pavon, and I am the technical lead of Kubernetes development at CoreOS. Here's some information about myself, but a little bit of introduction. I started at CoreOS about 6 months ago, a little more than that. But before that, I spent 3 years at Red Hat Storage, 3 years at NetApp, and about 12 years at EMC. So I've been able to be around storage for a long time now, everything from kernel development all the way up to services and RESTful services. So today we will be discussing how storage can be used on AWS with Kubernetes. We first are going to investigate how containers use storage. We then are going to talk about how Kubernetes uses storage services and how those services can be integrated with AWS. Later we will talk about and show a demonstration. And lastly, we will talk about something new, a new type of technology, which is called containerized storage. So there are really two types of applications that I run on Kubernetes at the moment. A lot of users are running what's called stateless applications. These applications have state, but they themselves do not manage it. Instead, what they do is that they let other services manage it for them. But there's a lot of applications that self-manage that storage and those services in that state. And a lot of these applications are around databases. These databases are installed and managed and need to contain and manage that state on some type of storage system. So there are really three types of storage. First, there's block, which is used for raw storage. And if you'll familiarize yourself with KVM, QEMU, OpenStack, OpenStack Cinder, and Ceph, and other things like that, you are very familiar with block storage. It's still also used in VMware for applications attached over iSCSI. It is then presented to the virtual machine as raw storage, and the virtual machine can then format that block storage and present it to the application as a file system. You could have a file system on top of block inside the virtual machine, or you could use a network file system like NFS or GlusterFS to be able to attach either virtual machines or containers to. Then there's applications that use object store, and this object store can then be managing petabytes of information over a simple HTTP interface. So in AWS, they provide these three types of storage systems. First, they provide the block storage called EBS, elastic block storage, and it can be easily managed and consumed from the AWS APIs. Later, we have a newer version, a newer type of storage system, the newest one. It's called EFS, or Elastic File Storage, and it is also available from Amazon to be consumed by its virtual machines. Lastly, we have S3, which is the object store provided by AWS, which provides a massive amount of storage availability. So let's talk a little bit about S3 and how it can be used in containers. Accessing the object store is actually quite easy from containers. All they need is the ability to have access to the network to be able to access that content on S3. And this is done over a simple HTTP protocol. So it's quite simple for these applications to be deployed on Kubernetes and then serve that content either through the application or redirect the client to that content. But we're going to focus in this talk mainly on the block store and the file store. And that is because those are the type of storage systems that are consumed or needed by databases and other applications that are stateful. So how is it that the storage is then consumed by a container? So let's break it down to its simplest thing. Let's talk about just a Docker container. When a Docker container runs, the host path or some directory on the host can be mounted on the host first and then be bind mounted and exposed into the container. But the host must have that storage mounted first before it gets exposed into the container. So in other words, we do not have the containers mounting the storage system themselves. We have the host mounting it first and then exposing that into the container. If the storage is going to be mounted and used in the container is a block, and the host software is responsible for not only mounting it, but then putting a file system on top of that. And the file system could be something like ext4, XFS, and others. And then once, again, it's formatted, it is then exposed and mapped into the container. And this is how container storage works currently. What if you want to do this at scale? So what we have now is to use Kubernetes. And Kubernetes can do the automatically, it can manage that storage for you. It can take block storage raw. It can then format it into XFS or ext4 and then mount it automatically into your container. It also has the services to be able to restart that container into another node and reconnect the storage that it was actually using. Lastly, it has services to be able to dynamically provision that storage and then provide it to the application wherever it is running in some node in the cluster. And there's brand new technology that was just added that also enables the automatic provisioning of storage, scaling of the application, and the naming conventions that are used in the network. And we'll discuss that in a little bit. But first, let's talk about the history of storage in Kubernetes. And this will give us an understanding of why we are what we are right now and where we're going in the future. At first, when Kubernetes started, it was a very manual process to be able to describe what storage system was going to be used for an application and how it's going to be accessing it. User, the administrator, had to describe exactly where the storage was, exactly how to mount it, exactly the file system to use, and then where to mount it. So it was quite heavy-handed. As Kubernetes matures in its storage management, it introduced something called persistent volume claims and persistent volumes. So persistent volume claims are an abstraction where the user places a claim into the system and they make a request of the storage. But at this moment, there is still no automatic provisioning of that storage. Instead, the administrator had created a pool of persistent volumes. And that pool of persistent volumes must have already created with some storage size. For example, let's say we created 10 block stores, each one of 100 gigs. If I only ask for 1 gig, it will give me 100 because that's all that's available in the pool. So it's not a very accurate way, but it's still a little better than before. As we go into Kubernetes 1.4, there's a new introduction what's called storage classes and dynamic provisioning. So now what the administrator can set up what's called a storage class that describes to Kubernetes how is it that it can provide the storage that is being requested. Now when the user provides or requests storage to you through a persistent volume claim, Kubernetes can then look at the persistent volume claim, look at the storage class that it has, and understand who or what storage class to use to be able to provide storage for this persistent volume claim. Once it is provided, it is bound to that persistent volume claim, attached to the container, and then the application can come up. When the persistent volume claim is deleted, Kubernetes automatically takes care of cleaning that up too and deletes the persistent volume and its storage. So later, we had what's called StatefulSets. So StatefulSets is a solution to one of the following problems. Let's say, for example, I wanted to create a cluster of nodes of some type of application, and they need to know about each other. Maybe it's a MongoDB application. So what happens is that with a StatefulSets, I'm able to scale the application as needed. And Kubernetes not only provides the storage that it's needed for that application through dynamic provisioning, but more importantly, it provides a consistent naming scheme. And that's very important because when those nodes come up, they need to know how to join the rest of the cluster. So now with StatefulSets, we have the following. We have storage that has been provided to us. We have an expected model of how to come up. And then we have the naming convention in the network that has been set up for us. So uniquely network identifiers are set up for you automatically. And what are those? What that means is that in Kubernetes, a service describes a reserved name, a DNS entry, where it doesn't matter where the container moves to, the access of that service through that name and through that DNS will always route to that container. The StatefulSets has something called a headless service. For each one of the containers that comes up as you scale up that application, a new name is created with the name of the application, the name of the StatefulSet dash and number. So what that means now is the cluster that you're creating, or the nodes as they come up, the containers as they're coming up, are able to find each other through DNS. Then we have the ability to have persistent storage. So the StatefulSet automatically consumes and it benefits from dynamic provisioning. And this, and the next part is really important because StatefulSets also describe and has a predictable order of deploying and scaling. And what that means is that you know as an application that the application name -0 will always come up first. -1 will always come up second. And actually when they go through deletion, they actually delete the opposite way. So it's a really nice way and predictable way to know how to join other nodes or other containers into your clustered application. So let's take a look a little bit as we now understand the usage of how Kubernetes uses storage, but how it actually delivers that internally. There are really two sections in Kubernetes architecture that manages storage. The first is called, the first manages connections, mounts of the storage systems. It manages the formatting of them. And that right now, it's mainly done through plugins. These plugins are part of Kubernetes today. There is a project called FlexVault, which tries to have a ability to be able to install external drivers, in a way, to be able to manage these connections for the storage system. But that flexible technology is going to be replaced by something called CSI, and I'll go into that in a little bit. Second, we have dynamic provisioning. So a storage system would need, it depends on the storage system itself, but it could need a plugin to manage the mounting of the storage, and two, what's called a dynamic provisioner. If the dynamic provisioner could be internal to the system, again, part of the Kubernetes code base, or it could be external. And there's a new project to be able to extend Kubernetes by being able to add these external provisioners at any point in time. So two things that I want to make clear is that the FlexVols are available today, but they are probably going to be replaced by something called the Common Storage Interface. And I have a link here to the proposal, which it's actually happening right now if you want to participate in those discussions. It is part of the CNCF and part of SIG storage in Kubernetes. The goal there is to provide a model for storage vendors to provide a driver or a way to handle the managing of mounting of volumes without being part of the Kubernetes core. Instead, being able to install it on demand. So that the really nice thing about that is that you can upgrade those containers. You get all the benefits from containers as you separate them from the main core of Kubernetes. Second, we have a link here that I provided, which is how provisions are starting to be created both externally, again, to the core of Kubernetes. I don't know if you've seen, but in the latest release of 1.7 of Kubernetes, a lot of work has been provided into Kubernetes to be able to extend it, not just from the storage point of view, but from the services point of view, from an authentication point of view, and so on. So now, let's take a look at EBS and how it integrates with Kubernetes. Today, using these technologies, what we as an administrator needed to do is describe which of the EBS technologies to use. And this is done through what's something called the storage class. Here we have the storage class. It's an example. And this example comes from the website of Kubernetes, the documentation. But in this example, what we're trying to show is that we name a storage class. And that name comes from the administrator. The administrator can decide that this is called slow or really slow or IO1 or anything like that. And then it is up to the user to change the persistent volume claims to be able to say that this persistent volume claim, this request for storage that I'm asking, I want it to come from this storage class. And then that way, Kubernetes knows where to get that storage from. So second, what we're going to type here for EBS specifically is that we need to decide the type of EBS volume that we're going to use. The default is GP2, but you can definitely feel free as an administrator to define the storage class to be able to point it to different types of EBS storage or different EBS storage types. We also have the IOs per second, which is only used for IO1 type volumes. And lastly, we have the encrypted volumes also that you can also provide as a storage class. Now, I think you saw that I skipped zones. And I'm going to go into that in a little bit. But before we're going to do that, let's show a little bit of the demo that discusses and shows how StatefulSets can be used in AWS. Show the demo here. The very first thing we're going to do here, I have a system running on Amazon. And I'm going to just show the nodes to show that they're working. Second is I'm going to show that there's a storage class and how it is defined. And you can see from the storage class that it refers to GP2 type volumes. Okay. Now what we're going to do is that we're going to show our application. In this demo, we're going to deploy CockroachDB. And what we have here is that our first part of our descriptor of our application to Kubernetes is the service. This is the public service. This is the one that other applications will refer to when they want to communicate with CockroachDB. The second one is what's called a headless service. And this one is the one used by CockroachDB nodes to find each other. And this is what helps the stateful class, StatefulSets nodes and applications to be able to find each other as the cluster comes up. And specifically, it can be done by setting the value of cluster IP to none. Okay? And lastly, what we're going to do in this application is show how the application requests storage. That is done by the what's called the annotation to use, let me go back a little bit past it. The annotation to be able to use the storage class that we just showed, which is the AWS volume, AWS storage class. So now what we're going to do is we're going to wait for the applications to come up. As you can see here, CockroachDB 0 is up first. CockroachDB 1 is up after, and so on. And we're going to wait until 3 of them are up. Once 3 of these nodes are up, actually not nodes, I keep calling them nodes, but actually containers. It could be running on any node. We're going to actually scale it up by 1 more. So here what we're going to do is we're going to say scale StatefulSet, and we're going to change it to replica of 4. So that's the new state that we want from Kubernetes. Kubernetes looks at the state that it currently has. It understands that it's mismatched, and it tries to adjust the state of the current system to be able to match the requested state. So here we have now 4 systems. Now what we're going to do is show through using DNS tests here, show how is it that we're going to look at applications through DNS. So we're going to use NSLOOKUP, and we're going to look at, for example, CockroachDB 0 and get the IP address for that. And we're going to see that the system has automatically created a DNS entry for it, and we can get back the IP for that. And the same thing for the others. We've got CockroachDB 1 and so on. Okay, so now what we're going to show is the number of persistent volumes that we've created. As you've seen previously in the StatefulSet description, we described to Kubernetes that the storage should come from the AWS EBS storage class. So these volumes that are here have all been dynamically created for this application. So the interesting thing here is that now that we can show the labels and we can show that where they come from. And one of the things you can see here is zones. So let me go into zones now. If you notice our storage class for EBS, you can define which zone to pin these EBS volumes to. You can define which multiple zones you want it to be, and the Kubernetes, as the dynamic provisioning comes in, it does a round robin of pinning them, each zone. But I didn't define any zone, so it took all the zones available in this region, and then it went round robin through them creating volumes. So we have 1A, 1C, and then again 1A, 1C. Lastly, what we'll do is delete the CockroachDB demo that we have here, this application. And what it's going to start doing is that it deleted the entire application replicas and containers. It shut them all down, but it does not delete the persistent volumes. And why is that? Well, when you want to do an upgrade of your CockroachDB or whatever application you're running as StatefulSet, and the number of replicas is down to 0 because you shut them all down, you don't want your persistent volumes to be deleted because that would be bad. You could not, then you wouldn't have a stateful application, whatever stateless application then. So now, it is up to the responsibility of the user to then delete those storage persistent volume columns once they are done. So in the demo, we go ahead and delete each one. Okay, we have nothing left. Okay, let's go back to our talk. Okay, so we understand now that we have an EBS volume and that it is connected to our containers. But EBS volumes have something that should be noted. It is that EBS volumes are only available in a certain availability zone in a region. So you have to be careful as an administrator or as a user also to make sure that your application is able to be used in a certain zone. There could be a situation where you have your application gets or moved from one node to another, but the other node that it moved to, due to, for example, reasons of resources and things like that, it goes to a node where the EBS volume that it was using cannot be longer attached. Therefore, the application actually will stay in pending mode forever until it gets restarted again into a node that is part of that availability zone where that EBS that is in. So this is something that should be noted. It should be understood when large applications are used in place. So is there a way to go around it? Well, you could use the Elastic File System. In the Elastic File System, for example, it's a really nice way to be able to consume storage. And I just want to point out that I see your questions, and all your questions will be answered at the end of the talk. So Elastic File System, it's a really nice storage system that's provided by AWS because it is just accessible using the standard NFS protocol, which is available in every Linux kernel. And one of the benefits is that it can be used across availability zones. So what are some of the issues with EFS? Let's take a look at them. First, you may have an application that requires more than 250 megabytes per second per instance, right? If you require more than that, then EFS is not for you. It's also not available in all the regions. When I was testing it, I had to take my application from US West to US East in North Virginia. Snapshots and backups are actually quite easy to be done and well understood in EBS. But it is not as impossible, but it's not as easy, again, with EFS. So if you have an application like a database that's running on top of EFS, and you want to take a number of snapshots and backups and so on, then you'll have to do a little more work than you would as if it was EBS. Now, because it's an NFS, they're really a provisioner for it. And EFS in Amazon doesn't really have provisioning either. You create one named EFS volume, and then it grows as needed and shrinks as needed. So as it grows and shrinks, one of the benefits about EBS is that you know the maximum size. You cannot pass this maximum size. So some systems go around that by providing something called. But today, have quotas. It may in the future, but it doesn't happen today. One of the biggest things to note is that it is almost 3 times as much as EBS. So as you use EBS, which you may find that provides a solution for your application, you just have to note the limitations of each one. So let's take a look at how EFS will be integrated into Kubernetes. First, it is not as simple as it was with EBS because EBS had a provisioner. With EFS, the administrator has to create the volume themselves. But more importantly, they have to actually set up the directory in that volume that they want to provide to the application. For example, if they want a directory for every application, maybe one directory for MongoDB, another directory for another database, or something else, those directories have to be created first. So you have to create some instance first to be able to mount the NFS volume, to be able to create the directory with the right permissions, and then after that, create the PV, which then can be consumed. So now here's, for example, the persistent volume claim that the user would place to be able to consume that persistent volume that was created by the administrator, to be able to take have the application use that. So that's how Kubernetes and AWS storage is integrated. So is there another model? Let's talk about containerized storage now. Our normal model of understanding of storage is the same model that we've been talking about for the last 30 or 40 years, which is we have compute on one side, and then we have storage in another. Normally, this is the same way we talked about with NetApp and EMC, where we had storage and so on. There's some type of I/O transport in between. But isn't a software-defined storage system just software? Couldn't that software-defined storage system be containerized too? And if we containerize that software-defined storage, could we have Kubernetes and manager of containers manage that for us? So that's where we talk about a new type of storage architecture, where we have Kubernetes as the data center operating system across all nodes, where it provides storage for your applications managed by Kubernetes, because those containers are managed by Kubernetes, providing storage back into the infrastructure of Kubernetes to be consumed by other applications. So in this picture, what we have here, if we have a set of nodes that have storage attached, and we have storage, containerized storage on systems that consume that storage and provide it back. Okay? Not just one cluster, but we will have many clusters managed by many types of individuals. We could have a cluster. We could have a minion cluster. Many types of clusters that are software-defined. And then we have the nodes that not necessarily have EBS volumes attached to them, instead consume the storage from the storage nodes. With this solution, you avoid these issues with availability zones, because now what you're saying is that these nodes are accessing your storage over the cluster network that's provided by Kubernetes, okay, or through the network that's available through AWS. Okay. So who's doing this? We got a couple of companies that are actually doing it, Portworx and StorageOS, and actually seeing this as a growth and seeing it as new technology that's changing the way we think about storage. We also have two community projects, one led by Red Hat, the other group led by Quantum, that see this model also and want to take advantage and want to containerize storage and provide it back to Kubernetes. So I have a live demo that I'm going to show where I have my own Kubernetes setup in AWS, and it is running GlusterFS containerized on AWS. So what I'm going to have here, I'm going to show you, is here I have my Tectonic cluster, and I have a namespace that I created called Gluster, and in that namespace I placed all my Gluster containers, and they are consuming EBS volumes. So why would you want to do this? One is you avoid the availability zone issue. That's very important. Why else? Another is the reconnection. You can reconnect very fast. The network is all through Kubernetes, right? You don't have to actually attach and detach to a virtual machine. What else? Well, you could take advantage of the technologies of the storage system that you deploy. For example, if we wanted to use geo-replication with Gluster, take data from one of the regions and then have it copied and backed up to another region, right? Or locally to your data center locally on-premise. As one GlusterFS cluster communicates with another. So it's a lot of advantages you can take. Now again, you have to manage. So there's pluses and minuses, but this is something else that is available there. So let's take a look at deploying an application. So on that system, so we're going to use kubectl, get nodes, to make sure everything's running and I can communicate with the system. This is all live, so hopefully nothing fails, right? So, okay, so we have kubectl, let's look at the storage classes. Here we have storage classes. Let's take a look first at the one for AWS, EBS. And we have here that we're going to use, if somebody uses the storage class, they're going to be using GP2 volumes. Okay. Now we're going to use the same thing, but let's take a look at the one from Gluster. And here, the storage class tells the plugin, the provisioner plugin in Kubernetes, how is it they can dynamically provision storage from Gluster to the application. All right, let's clear that. So we have an application here, it's called CockroachDB, the same one we saw in the other demo. And in this application, we're going to go down to the bottom and we're going to see that our storage class is going to be AWS EBS. Okay. So we're going to deploy this application. We're going to create first kubectl a namespace for it. Create namespace. We'll call it CB AWS. Okay. And we're going to deploy in that namespace CB AWS, create -f the CockroachDB demo. So this is how now the systems are deployed. And now we can take a look at the pods that are coming up. And here they come up. Let's show the node and show. Yes. Okay, so they're coming up. You know what? Let's deploy CockroachDB again, but now using Gluster Store. So let's go to storage class. It's called Gluster QM cluster, the storage class. So we're going to go here. I'm going to replace it with cluster, cluster. Let's make sure of that. I just like to make sure before I do this. Cluster.qm.cluster. Perfect. So now we're going to create another namespace for this one. Namespace CB Cocos C cluster. So now we'd say, I don't know, what did I call the other one? I already forgot. Get namespaces. Okay, CB cluster and CB. Okay. So now I'm going to say kubectl create. Let's put it in that namespace, CB cluster, and let's say create -f course. All right. So let's go over here and let's take a look at our namespaces that we have. We have AWS. We're going to look at our pods, and there's CockroachDB running there. Happy, using EBS volumes. Okay. All right. So now we're going to go into our CockroachDB running on top of cluster. And there they come. Excellent. So what this is now is that applications using dynamic provisioning have been able to consume storage either coming from AWS or containerized storage coming from Kubernetes itself. Let me go back to the slides. And come back here. All right, thank you for attending. And now I'll add, if you have any more questions, I also placed here some of these slides came from a presentation that myself and my colleague Kukulinski did at CoreOS Fest, and that is available there, link. So now I'll be looking at your questions, and I'll be answering them. So let's see. Will there be a common interface to specify backup and snapshot strategies? Now, I'm guessing you're not in Kubernetes or in AWS EFS. So I'm going to answer both of them. If it's in Kubernetes, there is work right now to have snapshot support as part usable from the user's point of view, in other words, through control of the PVCs. So that way the user can decide when to do a snapshot of their volume of the storage, as long as the storage system supports it. But it'll be done through Kubernetes. That is in the works right now, and if you want to participate, that would be great. It's available through the SIG storage team in Kubernetes. Now, if you're talking about EFS, then there is a very well written document in AWS that defines how to set up your backup and your storage for databases and such that use EFS. But thank you, that's a very good question. Let's see here. Which version of Kubernetes could you use the storage class descriptor with? Okay, the storage class descriptor can be used on any version of Kubernetes after 1.5, if I remember correctly. So 1.5, 1.6, 1.7 that just came out, you should be able to use those. Okay, in the scenarios like multiple pod constituting application, sorry, StatefulSet, is the pod using the PVC expected to run on the same zone where the volume is mounted? And that is correct. If you're running, and this is what I talked about before, if you have a pod that needs to access its EBS volume, then you must run that pod in the nodes that are in part of that availability zone. And that can be controlled for a number of ways.
Well, it looks like Luis got disconnected from the webinar, but thank you everyone for joining. If you have any questions, we will follow up with you, and this link should be sent to your email by today, I believe. Everyone have a great day. Thank you.